this should be mainly refresh for you, but refresh is not bad. Also, during the break, Ross was interested in some of the Bayesian modeling, and I found, actually, I Googled Bayesian methods in psychology, and there's a nice chapter on the web if you want to see the applications of Bayesian modeling for psychological research. Remember good old two-way ANOVA, everybody?
We do.
All righty. Yeah. Minimally, you had 2 IVs, and each one had minimally how many levels? Here, I'll help you. 2 by 2. Right? 2 by 2 is the minimum one. And using Keppel and Wickens notation, not everyone does, but you had a main effect for A, main effect for B, and the interaction. Remember that from good old 6021, everybody? Remind me again what an interaction means. What is the meaning of an interaction? Let's say for the simplest 2 by 2, let's just have let's go ahead and have
Your board right now.
let's have A, 1, 2.
Dr. Glaser.
Yes, sir.
Your board.
Oh, thank you. Thank you. Thank you very much. B1, 2. Let's say this will be those who had EQ training, emotional intelligence training. No training by male and female. And the DV is leadership performance, some type of measure of performance. So what does the 2 by 2 tell me? What does the interaction tell me?
That the effect of one variable affects the strength or relationship between the other one.
Okay. Can you be a little more specific, Zach?
So in that example, what's your A?
My A is you had emotional intelligence training. So you went to Talent Smart from one of our wonderful graduates, Gene Greaves. You had training versus no training, male, female, and the DV is some measure of leadership performance.
So the measure, your DV is affected by the relationship between being male and female and emotional training.
Okay.
So maybe the males or females have leadership measure is more strongly affected by the training.
Okay, good,
So
good.
females maybe, or like males maybe, females are already very well equipped to handle emotion, so maybe males have.
You know what? See, you just made me think you could do a Bayesian approach to this.
Yeah.
You put in those parameters what you think they are. That's almost a Bayesian thinking, right? If you think about it, a Bayesian, you put in maybe different means, assume maybe uniform probability, assign a probability for certain means for each of these, and that's how you could probably apply this to organizational outcomes. Because he almost already had an idea. You could assign a probability to each of those, a prior probability or a uniform probability. You do a Bayesian, so you could do a Bayesian approach for that. So that being said, basically what he's saying is that the relationship of maybe training and leadership performance depends upon your sex. Or the relationship of sex and leadership performance depends upon training. Though the other one makes more sense vernacular, doesn't it?
Yeah.
The relationship of training and the DV depends upon if you're male or female. So that's the interaction. Which part of the cells? The main effect of A focuses on, right? What are those called again? What type of means are those called?
Main effects.
This would test the main effect, and technically these are called the marginal means. Right? These are the marginal, and these are the what, everybody? The cell means. So the interaction focuses on what?
The cell means.
Yes, the interaction focuses on the cells, right? This should all be secondhand to you from 602.
Well, yeah, it's not secondhand, but I remember it.
Okay.
Used it a few more times.
Oh, there you go. So here let's have an ANOVA. Let's have a two-way ANOVA from a non-experimental study where you have male, female, and do you smoke, yes or no? And the outcome is self-efficacy. So then you have the four means. Happy or sad with Levine?
Happy.
Yeah. Why does he have 3 degrees of freedom?
He has 4 variables.
Not 4 variables.
4 cells or whatever.
Yes, 4 cells, 4 groups.
Yeah.
Right, exactly, 4 groups. And here are the 3 tests of significance, none of which are significant, but just gives you an idea. Right, demo 1 is smoking. We see we don't have significant main effect. Less than 1% is accounted for. Half of 1% is accounted for. The next variable, sex, and the interaction, 1.4%. What's interesting though, even though nothing is significant here, do you see the interaction has a stronger effect size? Which means sometimes can you gain power even if the main effects are not significant? Is it still possible to have a significant interaction even though the main effects are not significant? Absolutely. So it shows again kind of the synergistic, right? Synergistic properties of an interaction. Because if you think about it probabilistically, everybody, thinking of conditional probabilities, the probability of y, a comma b. Do you see how I wrote this conditional probability? The probability of y given a and b. Is that a possibility that that's going to be different than just probability of y given a? Is there a possibility that the probability of emphysema, given you're a smoker and sex, might be different probability of emphysema just if you're a smoker?
Yes.
Right? Once you add sex to the model, right, it becomes a very different type of model.
Indeed.
See, that's another thing when you get some Bayesian modeling. The sensitivity of those models, when you add parameters, not add parameters, and the probabilities associated with all those combinations. So, I know a lot of books use a line graph, as we discussed a year ago. And I told you my boss only let me do bar charts. Right? Remember, all the books do line graphs because he said they assume visually there's a continuity. Here, these are truly what's called a fixed factor. A fixed factor. So there you see if you're male, right, and a non-smoker, you tend to have more self-efficacy. And the lowest is if you're a smoker and you're male, you have the lowest. But again, you can see they're not significant. I also would encourage you, though, to usually use some type of error bar. Right? Remember, I was a big fan of error bars because those not only show the means, they show the variability. So, as you know, you can go way beyond this, right? You can do 2 by 2, 3 by 3. Right? What if you have 3 groups of employees by 3 types of leadership style? Right? 3 groups of employees, 3 types, and you get a P of 0.035 for a 3 by 3. Do you recall what we did next in 6021? Let's say you have significance for a 3 by 3. You did it by hand. Oh, so fondly. Here, I helped you out a little bit.
It was a year.
The opposite.
Ross,
It's
the
the
other most
opposite.
recent.
It's like 3 months ago.
Too much stats crammed into my brain.
It's the opposite of complex.
Simple! Oh, yeah, we hated those.
Oh, brother.
Now I
I
remember.
don't recall soliciting your opinion. So, that being said, so you have a 3 by... You guys, how long does this stuff stay? Is there like a terminal date?
It's about till we got. That's
Yeah.
CFDs are in November, right?
I took 5 years of Spanish. I can say a couple sentences, you know?
I'm sure you can.
You gotta work it.
Yeah, huh?
And we don't work it in our other classes.
Well, then you know what you can do?
Oh no, this is gonna get us in trouble.
Oh, shit.
Then you dummy up data and do it on your own.
Yeah.
That's
We have
what I
so
did,
much
but
free time.
I bet I could find filler. I bet I could find some filler time when you're on Facebook or something
Oh,
like
you
that.
get this extra credit.
I
That's
do extra
incentive.
credit. It goes against every bone in my body.
Oh, you and your bones.
We're getting older, believe it. Such an 8 right here, man. So we have a 3 by 3.
You got an eraser elbow?
I got a whiteboard. We were not on film. So, do you remember being able to do 3 simple effects? This would be A at
3.
B what?
Oh.
A at B. So you have three simple effects.
Is this where we 0, 1, 0?
No, you're thinking of plan comparison.
Plan comparisons. How do you
And then you have three simple effects there, right? So what you see is if you do have significant for more than a 2 by 2, you can look at the, or even 2 by 2, you can still do it. You do simple effects. The interaction to examine where the significance is. So, page 273, 3 methods of analysis in text, and 4 from SPSS. We actually went briefly through the 6021. First, if you have equal sample size cross groups, they're all the same. Number 1, everybody, all these methods are exactly the same if you have equal sample size. In other words, if you have the luxury of 20, 20, 20, and I'll just do 60, 60, 60, you have 20 in each of these. It doesn't matter what method you use. So you're going to find there's 4 different types of sum of squares in the general linear model option in SPSS. The book only gets into 3 of them, but there are 4. GLM gives 4 convenient methods for computing sum of squares. Type 1 method calculates the reduction in error by adding each effect to the model sequentially. In other words, polynomial regression. Remember polynomial? What went on the first step in regression? You should know this right away, Ross. You've been just going on this.
I didn't hear the question.
Okay, polynomial. What went on the first step for regression? Which effect? For polynomial model. Chapter 6 of Code.
Main effect.
Okay. Polynomial.
The quadratic.
Okay, that went at which step?
The quadratic was on the second step.
So what went on first?
So linear.
Thank you.
Sorry.
Thank you. No, you were there. It just took a little coaching. So there you go. So linear, quadratic, etc. So you control for each step. What's that?
We hated
It
it.
sounds like you're hating a lot of it, Jocelyn. That's
Are
understandable.
your multiple personalities coming out again? This we talk.
So, type 2 calculates the sum of squares adjusting for all the other appropriate effects. In other words, it adjusts for the main effects. So first step would be main effects, next interaction. The type 3 is the default in SPSS. It deals with unbalanced models, is pretty flexible, so to speak, with missing data, with no empty, it can deal with unbalanced models with no empty cells. Do you guys know what an empty cell is?
Where the whole variable's missing, right? Just one missing value? I thought it meant
It's not just one missing value. It's a 2 by 2, and there's no one that was male and placebo. 0 people. All 22 people dropped out. Why?
awesome.
What if all 22 people dropped out? Why?
Because it's a placebo, they wanted the positive effects of whatever they're supposed to get.
There you go. In other words, do people drop out of studies, especially if they start thinking they're getting a placebo?
Sure.
Yeah, right. They want the effect. If they think if you have a good clinical trial, double-blind, placebo, randomized, they shouldn't know if they're getting it or not. But the fact is, if you have missing data there, which I'm going to actually discuss in my continuing education here on missing data, if you have what's called differential attrition, that means, you know what, certain types of people tend to drop out. You've got to examine that and see what the heck is going on. Technically speaking, everybody, there's actually a fancy term for that. That's called a structural zero. Sometimes the structural zero, we have what's called structural zero, meaning number of OBGYN male visits. Do you see why that's a 0?
Yes.
Right? So it's 0. So sometimes it's part of the model. And sometimes there may be planned missingness. In other words, company A gets the Meyer-Briggs, and company B gets the California Psychological Inventory. Sometimes you may have these types of planned missingness into the actual model. Type 4 sum of squares allows you to easily deal with empty cells. Type 4 calculates the sum of squares for an event based on the cell mean coefficients, almost like dummy coding. So what you have here, everybody, is in SPSS. When you go to the general linear model option, analyze, general linear model, MANOVA. And let me just go to the general linear model for now, just to make it easy. Analyze, general linear model, univariate. Under model, do you see this thing called sum of squares? The default is type 3. But here you have 4 different types of sum of squares. And that's what this chapter actually spends a bit of time discussing each of these. And
Type 4 is good for missing cells. Do you?
it does talk a little bit about that. It has some flexibility. It allows you to deal with empty cells. There's a hypothesis matrix L for an effect constructed for each row, and it can plug in a little 0 for that.
How often do you use type 1 or type 2?
What's that?
How often do you use type 1?
I almost always use type 3. It doesn't create that much of a difference. Type 1. See, what's weird about one of these is such that it'll look at the main effects as if the interaction doesn't exist in terms of it won't adjust for it. So that's why the book makes some recommendations that it seems like type 3 they like the best. So the default is type 3. What I want to show you, and there's the syntax, everybody. Method equals SS type, parentheses 3. Probably nothing you never paid attention to during 6021, including a good chunk of the class. So that being said, you have the multivariate test, type 3. You have the p-value, 0.011 for the main effect, demo 1, 0.472, 0.7, interaction is not significant. There's the default, everybody. There's the default. And we do have a significant main effect, right, for this MANOVA. So now we've done a factorial MANOVA with exercise and diet as the DVs, and we do see, drilling down, that we do have significant differences between the groups on exercise and diet for those who smoke versus non-smoke. Type 1 corresponds to method 3, everybody, in your book. Type 1 in SPSS corresponds to method 3, sequential hierarchical approach, the default of SPSS. And you can see here that there's a little difference in the p-values, everybody, not a lot. 0.005, 0.596, so there is a little bit different when you adjust for the sum of squares. They're still significant for the main effects. Type 2 sum of squares corresponds to method 2, as indicated in your book, called the experimental approach. It adjusts for the main effects. This one, it seems your author seems is not so hot on. But here again, significance there, but slightly different p-values, slightly different effect sizes, slightly higher effect size for smoking.
What does that mean, it adjusts for the main?
And basically the method 2, type 2 sum of squares,
Yeah.
it has the main effects and it doesn't adjust for the interaction. It's like you have a main effect model only, ignoring the interaction. Whereas the 2A ANOVA still takes into account that the interaction is part of the model and is incorporated in the error term when it's testing for significance. So it's going to be a slightly different error term.
Yeah, I just wasn't sure what adjust means
Yeah.
in that context.
And SS4, which is not in text, is good for empty cells. And we can see here it's pretty much the same as the first sum of squares. So everybody, I just wanted to show you, when all said and done, we see fairly similar results for each of these 4 sum of squares. Very, very similar, but they will somewhat depart as the extent of sample size and balance happens in your study. Usually you'll be fine leaving the default, but you can play around with the other ones and see if you gain more power. But the sum of squares 3 is usually pretty good. But these are the 4 different sum of squares incorporated in the general linear model. Now, that's a 2-way MANOVA. What about a 3-way MANOVA? 3-way MANOVA, you have 3 IVs, and minimally would be a 2 by 2 by 2 design. Minimal would be a 2 by 2 by 2 design. How many tests of significance do we have, everybody?
6.
7. Right? You have 3 main effects, A, B, and C. 3 2As, A and B, A and C, B and C, and then the 3-way. So you have 3 tests of significance. So one way of looking at this, everybody, just for a simple 2 by 2 by 2. For a simple 2 by 2 by 2. So let's have males, females, males, females. And then, within each of these, so you can see it's going 2 by 2 by 2, then you have maybe EQ training, no EQ training, right? And then, if you think about it, within each of these, right, you have EQ male, 1, 2, EQ male. So you have this 2 by 2 by 2. So you can have at least 8 means. And then you could have, within each of these males, you could have maybe clerical versus management, clerical management, clerical management, clerical management, something like that. It gets pretty complex. It gets pretty complex. I had a few of these I had to test for my dissertation. So let's say we look at stress, by low, by training, by raise, no raise versus raise. And visually, the only way to tell the story is showing 2 two-way interactions in separate plots. Otherwise, it gets very busy. So let's have demo 1, demo 6, and demo 5. Let's go ahead and just have these, just for illustration's sake, everybody. And as you know, I have all these syntax files, if you're at all interested, on Blackboard. So let's say, do you smoke? What is your sex? And are you currently in a relationship? So let's have 3 of those to look at the 3-way interaction. So here, there's, under the design syntax, there's your 7 tests. There's your 3 main effects, your 3 two-ways, and the 3-way. So, with 2 DVs and a 2 by 2 by 2, guess how many means minimally you'll examine? 16, right? 8 times 2 is 16. Gets a little busy, huh? Does everybody see why you have 16 means? 2 by 2 by 2 for each DV, and you have 2 DVs? So think if you have 4 DVs for your dissertation and a 3 by 3 by 2. You may have that, Jocelyn. You may have EQ training, a training that will be done online versus lecture versus versus what?
Hybrid.
Hybrid. You may have clerical versus management versus executives. You may have males versus females. There's your 3 by 3 by 2. And you may have 4 DVs. Job engagement, job commitment, job stress, and organization, job satisfaction. There you go. There's your 3 by 3 by 2 and 72 means. Would it be hard to make sense of 72 means simultaneously? It's a lot. So you can see these factorial models, especially factorial MANOVA, can get very, very busy. I mean, they can get busy. Here's just the 2 by 2 by 2, the simplest 3-way factorial. 2 by 2 by 2. So it separates it by X by yes, do you exercise, yes or no? Male, female, are you in a relationship, yes, no. So do you see, you got 8 means within for each of the DVs. So again, it takes a little bit of sleuth work to make sense of it. Here's your multivariate test. You have 7 tests of significance. You have a main effect for the first variable on smoking, which is significant. You don't have one for sex or in a relationship. And none of the 2 ways or 3 ways are significant. Sometimes you may be relieved when the higher order interactions are significant because it relieves you of having to write it up. But if it's part of your hypothesis, you're not so happy. Having a hypothesis with a 3-way is pretty complex. If you really do get adventurous and have a postulated 3-way, the one way that's going to make sense for your committee is to draw it, because it's the only way that you're going to be able to make sense of it. To literally draw maybe 2 two-ways. Right? Maybe to draw 2 two-ways. and have this be for males, this one be for females, and this be no raise, raise. No raise, raise. EQ training, no training. EQ training, no training. DV is leadership performance. It's pretty complex, doesn't it? This is the simplest three-way model. So here, if you're male and you get no training, look at this, everybody. No raise versus raise, they do better. Here, when you get training, they're the same, whether you get a raise or not a raise. For females, look at females. They actually went higher. Money was more motivating for performance when they got the training. No training there, received flatlining. So that's how you have to visually show. You can put it in words, but it's going to be quite a hefty paragraph. So I would always supplement a three-way model with these two-way graphs. Do you see what each one is a two-way interaction? Each graph is a two-way split at one of the variables. And then you have to make a decision, which variable should you split at? Should it be raise, no raise? Training, no training? For my dissertation, we had a few three-ways, and we're constantly redoing the graphics just to see which one would best tell the story. Sometimes if you have an experimental variable, then it may already be made for you. The experimental variable, probably placebo versus control. You probably have that there. But it depends what will best tell the story. And then, if you have significance for the multivariate test, if the multivariate is significant, then you're going to go to each of the effects, the main effects, interaction, and then you're going to see which ones are significant for which outcome. Again, the only significance is for those who are smokers versus non-smokers for both DVs. So here you see there's a lot to examine from a factorial MANOVA. But it's better than doing tons of ANOVAs, right? Much better than doing tons of ANOVAs. So if you have a multivariate significance for three interaction, you have to keep in mind the multiple DVs. Though drilling down into the univariate three-ways may shed insight in the nature of the interaction. See, let's say the three-way was significant. Then you would look at the three-way for each of the outcomes to see which one, if any, are significant. And if you have a 3x3, guess what then? You have to start doing simple effects analysis in a MANOVA context. Right? And if three-way, and if univariate three-way is significant, then consider simple effects. Definitely make liberal use of plots. If Maggie has a 2x2, 3 significant interaction with 3 DVs, she's got 36 means. There's no way I want to read a multi-paragraph narrative, you spitting out all 36 means. It'll make your reader go absolutely blind. But you can discuss patterns and maybe a few of the more appreciable means. Now, if you don't have significant three-way, then your attention turns to what, everybody? Yes, the two ways. Then your attention turns to the two ways. Right? From one to all of them may be significant, and you have to summarize all of them. And again, drilling to the univariate two ways may help illuminate the fallings. Now, what if no multivariate significance? We go ahead and interpret the highest order univariate. Now, to add to the complexity, what if you have significant 3x3 x 2, and you have significant for each univariate across all DVs? What next? Simple effects. And what if your simple effects is significant and you have greater than 2 groups? Then simple comparisons. Do you see how complex it potentially gets when you have these factorial MANOVAs? It really is the same as ANOVAs, it's just more of. And as you recall how to do simple effects, remember the wonderful little syntax I showed you, everybody? Compare and the adjusted. Remember, this is syntax only. To conduct. simple effects analysis. And there's the multivariate test. There's the multivariate test, everybody. For do you have health insurance? And those are people that smoke, and the sex, male and female. And here you can see you get the test of significance. Male, female, do you smoke, do you not smoke? And there's your simple effects analysis. So you can get all of this in SPSS, everybody. So there's nothing you can't do in ANOVA that you can also not do in MANOVA. It's just more of it. It's just more of it. You can do all that analysis for these factorial models. Any questions in just this brief discussion of MANOVA and factorial models? Okay, let's move on then to chapter 9. We are on schedule and maybe a little ahead. Obviously, what I'm hoping is, as you know, you were short-shrifted one class this semester. I'd love to give you the opportunity to do the presentation on SEM. And again, we're playing that by ear, just seeing how far we get. And COVA. We already did this in 602.1, but it was the last lecture. It went a little on the fast side. Now we're going to explore this more, and also you're going to learn about MAN-COVA. Now you're going to learn about MAN-COVA. So you had ANCOVA, and of course you're going to have the multivariate extension, MAN-COVA. Can you remind me again why we would ever do an analysis of covariance? Does anyone remember why we would ever do an ANCOVA analysis? Anyone?
That was our
Last lecture.
winter break lecture, I think. Our makeup lecture.
Anyone remember? So let's say I have a treatment variable. I'm going to call it T. I have a treatment variable that maybe, assumedly, impacts the DV. Right? Everyone clear on that? X is a covariant. Is there a chance that there might be a third variable that in part is related to the DV? Is there a chance that there might be a third variable that's related? And if I can go ahead and partial away that X, if I can maybe partial away the variance, the covariance, and decrease. What does MSE mean?
Some type of error.
Okay, can you be a little more specific?
Mean square.
Thank you. Mean square error. See, 6021 coming back.
Yeah.
Okay, excellent. So would it be nice to decrease or increase error?
Decrease.
Yes, you got it.
Yeah.
So that's why often used simply as an alternative name for explanatory variables, but perhaps more specifically to refer to variables that are not of primary interest, is the covariate. So what is a covariate, everybody? Sometimes it's exploratory or explanatory, but it's measured because you think it's likely to affect or be related to the response variable, and you need to be included. So this is from a wonderful dictionary I have called the Cambridge Dictionary of Statistics and the Medical Sciences. I have about 3 or 4 different statistic dictionaries, each of which has its own idiosyncrasies. So this is kind of a cool definition. Here's the Dictionary of Stats and Methodology. This is a great one for psychology majors. Wonderful, non-technical dictionary. Another term for IV, covariate, a variable other than the IV that correlates with the DV. Typically, the researcher seeks to control or subtract the effects of the covariate. Exactly what I did there by using techniques as regression or concova. Sometimes it's called the concomitant variable. So, for example, you're comparing those who received training on Word versus those who did not. And the DV is computer performance on the job. But someone says, did you control for prior computer experience? Could that be a covariate? Are some people more comfortable with Word than others? Especially in the old days when computers were still kind of new, some people just had a facility with being comfortable with computers. Some were terrified. So, maybe you might control for comfort with computers. I remember the first time I got a computer in the 80s, I think it had 755 megs in memory. That was bigger then. And so now you can hold it on a much more, right, a thumb drive, obviously. So then I remember putting the computer in my house, and it was like having a pet python. I didn't want to be near it. And I just didn't know what to do with it. And so you buy one of those 1,200-page books that say a gentle introduction to DOS. Because, you turn the computer on and you get a C prompt. So that's what you did back then. And it was really a pain to learn. And we didn't have Word back then. We had WordPerfect. So you did all the function keys, Control F9, Shift F9. I got rid of 20 pages of my dissertation once, making a mistake on Shift F9. I was working all night on the tables. I hit Shift F9 in those, and it said math on the lower left. Got rid of 3 hours of work on my tables. I was saving, but I didn't save enough. So that being said, people have different level of comfort with computers. So there may be third or lurking variables that may explain between group differences. And that happens a lot, everybody. Think if you want to do a study examining, you do an intervention or a training. I'm going to do emotional intelligence training, and that's my predictor, so to speak, explanatory. And my DV will be commitment to the organization after they've had the training. What might be related to organizational commitment for a bunch of leaders that just got training? What might be related?
Salary.
Okay, maybe salary. What else?
Tenure.
Maybe number of years they've been there. Right? Tenure in years, absolutely. See, there's some overlap. You get to partial that out from the unexplained term, the error term. So there's a reduction in error that can happen. So, what are the purposes, everybody? One, eliminate or reduce systematic bias. I would prefer to say reduce. I doubt you're ever going to eliminate systematic bias. I don't think you're ever going to completely eliminate it, but that's one option. The book says elimination of systematic bias. I'd like to temper it and say reduce. Number two, reduction of within group or error variance. The mean square error. And if we reduce error variance, which error goes down, type 1 or type 2? If we have a decrease in the mean square error, which is the denominator for ANOVA modeling, and the error is smaller, which error is reduced? Type 2. Right? Because remember, type 2 is the complement of what? Power. So if I reduce it, guess what? I've decreased type 2 error. I've decreased type 2 error. Or concomitantly, I've increased power. Right? So we have more power when we decrease error variance. And MANCOVA is the multivariate extension of ANCOVA. This is the linear combination of DVs are adjusted for differences in the covariance. The linear combination. And you will be doing a MANCOVA for your take-home, your second take-home. So, that being said, there's a lot of advantages afforded by finding a variable that's related to the outcome that may prove to be a confound, a covariate, or explanatory variable. Now, true, if you have true random assignment, or sometimes they use the term random assignment, or a lot of times in medical studies, they'll call it allocation. They'll call it allocation. If you have perfect random assignment, everyone should be equal on all these variables, right? If I have perfect random assignment, and 30 people get training, 30 people get no training, and I have random assignment for each of these. If I have random assignment, they should hypothetically be equal on all these other ancillary variables: intelligence, athleticism, depression, anxiety, how many years, tenure, their age, their salary. But does random assignment always work perfectly? No, I mean, it'd be nice, but sometimes it doesn't. Because remember, it is random. It is random, which doesn't necessarily always guarantee the process. Believe me, I've seen it happen. Even with random assignment, sometimes you still get between group differences. But that being said, random assignment is one way of being able to deal with systematic bias. That's one way that's ideal. But a lot of times, we don't have the luxury of random assignment. So, anyone of you going to drive on the freeway tonight? Anyone going to be on the freeway when it's darker? Okay, I'd like you to have 6 beers, 3 bong hits, speed 80 miles an hour, and text while you drive. Okay?
So does a normal Monday night time.
Okay, and my DV will be in epidemiology, what's called mortality. What does mortality mean? Be live or dead, right. It's a binary outcome, which you can use for discriminant function analysis. Do you think I can randomly assign any of those conditions? Do you think there'd be some ethical concerns? But do you think the Center for Disease Control and or our crime labs have data on who's texting and or drinking while they drive? In fact, texting is, as the research from University of Utah shows, texting is bad as drinking and driving in terms of being distracted. So a lot of times we have what's called quasi-experimental studies. Or in medicine, they have a thing called case control studies, where you see how many people maybe have swine flu versus those who don't in a similar area. Because you can't sit there and randomly assign them to get swine flu. How many of you would volunteer for that study? Not many in the back. You're going to volunteer? No, probably not. So, but a lot of times we know certain things may be associated with those outcomes that we can statistically control for. And I'm going to discuss the use of a covariate in experimental versus non-experimental studies and pros and cons of each. If you have an intervention for a spelling tutorial for a second grade, and those in room 1 get the tutorial, and in room 3 they do not, where's the potential bias? So let's say there's no way a teacher is going to let you come in midstream and randomize the kids. Where's the bias? Room 1 gets the tutorial, room 3 does not. So maybe I still randomly assign the intervention. Eeny, meeny, miny, mo, you get it, you don't. So I can randomly assign the intervention, but I can't randomly assign what? Yes, the individuals. So, where's the bias? And then I find, wow, room 1, those who got the tutorial did better than room 3.
They may have already been in the smart class.
They may have already, absolutely. So what might be a good covariate? You kind of answered the question, Chad. GPA. What's that?
I was going to say grades prior to.
Absolutely. Spelling ability, right? Or maybe even more focused. Spelling ability. Absolutely, those could be. So analysis, what you're going to find in COVA is ultimately on the adjusted means. The analysis is not on the obtained means for each group, but on the adjusted means. Let's say I have 3 groups. Do the slopes look equal?
Yes.
And do you recall from the ANO and COVA lecture what assumption tested that? Does anyone remember? Something with slopes. Homogeneity of regression or homogeneity of parallelism. We're going to discuss that. Again, there is some controversy about the use of covariates with intact groups versus use of covariates, and we're going to discuss this later, in random assigned studies. Some people think when you have intact groups, it's inappropriate to interpret adjusted means because the groups are intact. So there's really different opinions, but that's when a lot of people use it because you don't have the luxury of random assignment. So, here everybody, what if age is a covariate? And self-confidence is my DV, and these are males and females. Do the slopes look different? Yeah, we're going to talk about that. That's a visual capture of the assumption of homogeneity of regression. And we'll discuss that you can test easily in SPSS. So here, what it ultimately does analysis on is not the actual means, but the adjusted means. And we're adjusting based on what? Each group's age. And I'm going to show you the math behind it. First step, everybody, there should be a substantive correlation of the covariate and the IV. And for MANOVA, right? And for
Hang
MANOVA,
on, the covariate and the IV or the DV?
the covariate and the DV.
DV.
Yeah, yeah. And for MANOVA, MANCOVA, relationship of what? Of covariate and DVs. Yeah, so the covariate and the DV. Right, that's what you want the relationship of. Because if you recall, Chad, a covariate is only worth it if it's got a relationship with the outcome.
Right.
Because what you want to do is be able to partial away that error variance from the mean square error term. It doesn't make sense to control for a variable that ultimately will reduce error variance if it's not related to your DV. And what is a substantive correlation? I don't have an answer, as I say. I mean, you'll see some textbooks that say 0.3. You'll see some textbooks that say you should have a correlation with 0.3, which means what percent is shared variance? What's that? 9%. Really different opinions. Some say it should be a lot higher, but some will say R, X, Y, where X is covariate and Y is deviant 0.3 would be good enough, 9%. So let's look at self-efficacy. It's a term used in psychology corresponding to belief in your own competence. That doesn't mean that if a kid feels they throw the ball up and they can hit it, that they're going to hit a home run. That's called outcome expectancies. But enough confident that if I throw the ball up, I can at least what?
Make contact.
Make contact. Absolutely. Absolutely. So let's go ahead. How many hours do you exercise per week? And self-efficacy is my outcome. The correlation is 0.27. And that's real typical what I see when people use covariance. There's 7.02% shared variance, so it's not bad. It is significant, but remember, don't always rely on p-values. Don't always rely on p-values. Look at the correlations, look at effect sizes. So it's a moderate, right? It's a moderate effect size. It's a moderate effect size. So now, is there a chance that if you think about it, how much confidence you have that you can perform an action might be related, let's say especially with health, how many hours do you exercise per week? Right? And there is a relationship there. There is a relationship. In fact, this is actually pretty germane. Maybe not to your age, but old farts like me. Because all of a sudden, you got some cardiac problems, you go in for your checkup, and all of a sudden you've never had a regimen of exercising. And all of a sudden your doctor says you need to start exercising 3 times a week for 30 minutes. How many of you have exercise regimens? Okay. Would it be hard for you to start?
I mean, what do you mean by regimen?
At least
Yeah,
3,
like
4 times a
like
week.
set schedule?
Yeah, almost set, pretty set.
I mean, I exercise 3 or 4
Okay.
4 times a week, but it's not like on a regular.
Do you think it'd be hard telling someone who's 56 years old, who really doesn't exercise that much, doesn't like it that much, and all of a sudden they have to start working out half hour a day, 3 times a week?
Yeah.
Absolutely. That's a big change for them, and it ain't easy, right? So that being said, you can see that if they feel confident that they can perform these exercises, not become an Olympian, but that they can even perform the exercises, maybe having a lot to do with self-efficacy. One older Ed Psych article indicates if R is greater than 0.3, okay to proceed with MCOVA. Also, if you have a randomized design, MCOVA possibly may not be necessary if it went perfectly, right? If it went perfectly, the units should be on the same, right? All the units should be the same, units meaning people, on the covariance. So let's do a one-way NOVA for comparison. Let's have self-efficacy by are you in a relation, yes or no? So does everybody see that we don't have significance? You see the P of 0.437, the F of 0.61, and do you see the mean square of the error of 0.605? Does everyone see that mean square error? And looking at a formula on page 291. Let me show you how you can adjust it for the covariate. There's a couple ways of showing it, but mathematically, this shows you part of how it's reduced. What if I took the mean square, remember that 0.605? The mean square of the within minus the mean square of the within, r squared times r squared. Meaning, I take We already know 7.2% of the variance is accounted for, which is the relationship of x and y. And just multiply that by the unexplained, and it's 0.565. Oh, what does that tell me, everybody? That there's going to be a change in the error term based on the relationship of the covariant. In other words, mean square error times 1 minus r squared will show you the change. And mathematically, you can see what happens if I have a useless covariant. The correlation of a useless covariant will be 0. What's 1 minus 0, everybody?
1.
Excellent. Excellent. It was not a trick question. 1 times the mean square of the error will equal 0.605. Right. So you see, if you have a useless covariant, I haven't reduced the error variance at all. Now let's look at a strong covariant. Let's look at 0.8, just for funsies. Goes all the way down to 0.12. The initial error term, mean score is 0.605, huge change when I have a stronger covariant, which means you're going to gain or lose power. Decrease type 1 or decrease type 2?
Decrease type 2.
You got it. Okay, everybody. So here you get a preliminary argument for the strength of covariance. You need to limit the number of covariants. I've been on studies where generically when I was in Sharp Healthcare, they used to always control for age, sex, and number of comorbidities. Comorbidities is number of illnesses they have, especially with heart failure. But the fact is, I can tell you many studies, there'd be minimal relationship. And things get really complex when you have multiple covariants. And I'm going to even show you ways you can test these assumptions with multiple covariants for a MANOVA or MANCOVA. Plus, you run the problem of linearity amongst the covariants. If I control for organizational satisfaction, organizational commitment, and stress, those are going to be related, just like any regression model. There is a little formula that they actually show you about what will be appropriate. Where C...
Is it officially called Little Formula?
This is, yeah. No, it's not. It is a small one, Smarty Pants. C plus, but that was a very helpful comment, Jocelyn. C plus J minus 1.
Well, if I Google Little Formula.
I know. And you know what? We can even Google little grade for Jocelyn. So C plus J minus 1 divided by N, where C is the number of covariants, J is the number of groups. So if you have 2 groups, and if you have just, say we have just one covariant. 1 plus 2 minus 1 divided by sample size is 0.0137. So the book says it'd be great to have it less than 0.10. It's a formula. It's a little formula. That's used for sometimes saying if you have too many covariants. So what if you decide I'm going to have 5 covariants? What if I have 5 covariants and you have a sample size of 100? You'd still be okay. But remember, if you have 5 covariants, are they going to be related?
Yeah.
And you guys, I know that may sound like a lot, but I've been on healthcare studies where they want to control for systolic blood pressure, creatinine. Are they on beta blockers? Are they on ACE inhibitors? And control for blood glucose. Do you think any of those might be related? Absolutely. Absolutely. That's why sometimes they come up, I don't know if you heard the term a risk-adjusted score, or you'll see that a lot in the medical domain. They say adjusted for severity illness, adjusted for blood glucose, COVA is doing. It's adjusting. So when you have a risk-adjusted score, you're adjusting for these other variables. Well, fine, you don't want too many covariants because it gets deducted from the degrees of freedom in the error term. Because mean square error, as you may so fondly recall, is a function of sum of squares within, degrees of freedom within. What happens if that gets smaller? My error will be bigger or smaller?
Bigger.
Yes. And if my error is bigger, increasing type 2. Which means if I have a useless covariant and I have multiple covariants, if I have 15 there and I have 1 covariant, 14. 2 covariants, 13. 3 covariants, 12. And unless it reduces that part, if it doesn't concomitantly reduce by sum of squares, because they yield small correlations, you're actually going to be shooting yourself in the foot and actually compromising the power with a technique that's supposed to increase power. And we don't want to do that, do we, everybody?
No.
Okay. So if the sum of squares is the same because you ain't got much of a correlation with the outcome. And I go from 4 to 3 degrees of freedom. Look, my error term actually gets bigger, which may seem counterintuitive. But that's what happens when you have a bunch of low correlations of covariance. Big thing with experimental designs, everybody. Measure the covariant before your intervention for experimental designs. Measure them before they are in any way contaminated by the intervention. Now, if it's a quasi-experimental study and you're controlling for age or sex, I seriously doubt your age or sex is going to change radically by the non-intervention or the explanatory variable. But if you have a true randomized study and you have a second-grade spelling intervention and you would control for intelligence, is there a chance that IQ might be influenced by the intervention? Right? Possibly, right? There is a chance. And if so, if the treatment influences the covariance, that will add bias. So make sure to measure the covariant before treatment, right? So especially for CRTs. What does CRT stand for, everybody? Controlled, randomized trials. There you go. Excellent. Excellent. So, although if a covariate is a time-invariant variable, such as sex, then it doesn't really matter when you measure, right? Or for non-experimental studies. Or for non-experimental studies. Though, there are exceptions. What I was thinking of is maybe case-controlled studies, where maybe you want to look at swine flu, those who were exposed and got swine flu versus not. There might be some variables you might want to think about that were measured before they were exposed. In fact, weren't there about 3 deaths up at Yosemite with hantavirus this year? Weren't there a few deaths? And it's because apparently they breathe in the spores of these fecal matter of rats. And a bunch of people were exposed to it. A lot of people were in the same cabin, but some people died, some did not. So there might be some things you can think about, like maybe, do you think they might have records if they have any allergies? Right? You may have some records before they went to Yosemite about maybe some type of allergies or something before they were exposed. Step number 2, assess the linearity of the DV and the covariant, which means scatter plot. Do you guys remember those wonderful Lois graphs?
Yes.
Yes, and what does that stand for, Lois?
Least ordinary.
Locally weighted, smoother scatter plot.
Oh.
Wait, say one more time.
Locally weighted, scatter plot smoother. Lois, L-O-E-S-S. Right.
Where's the W then?
Where's the W? Well, it's L-O-E-S-S. The other one, L-O-W-S-S, may use sometimes weighted, locally weighted, scatter plot smoother. There's L-O-E-S-S and L-O-W-E-S-S. That'll drive you crazy. So here,
OMG.
what's that?
OMG.
Okay, and so we're almost done, you guys. A couple more minutes, and then you're free to go. You're hanging in there. You're doing a beautiful job, Bird. We would love there to be a linear relation, and impose the lowest line. And so you do the linear relationship of the covariant and the outcome. Again, just a nice visual, because if it's nonlinear, you may want to consider some polynomial options.
See, but those clusters,
Yeah, well,
that doesn't look linear to me.
I know, but it's...
But it is there at the end with those.
Yeah,
those
and it's
few.
because you're right, because we got a lot of clustering of the scores that went in, but the variability because most people exercise less than 10 hours. Now, you know, it'd be interesting is just cut it at less than 10 hours and then see, right? And then see. It might look a little bit different.
Dr. Glaser, I have a kind of unrelated question. If you look at a scatter plot and you see an outlier, is there a way to, like if it's not something, like if it's not
let's say it's right there.
Yeah, if it's not a metric that's as easy as like 40 hours or something, I forgot what I was looking at, but there was something where it was like a standardized, I was looking at standardized scores, and there's like a standardized residual, and like there was some value that was way off. Is there a way to find out what value that is, or like what case that is?
Absolutely. I mean, one thing you can just do, just for that variable,
Mm-hmm.
just that variable in isolation.
Mhm.
You could just do the z-scores and see if it's greater than 3.0, see if it's an outlier, just for that variable itself.
Mhm.
In terms of the variable of the plot, then you could start looking at the standardized residuals, do a regression and look at the standardized residuals, and if it's on the set of predictors, look at the leverage. So there are the host of those. Those actually a host of statistics to look at the outliers. Otherwise, if transformations don't help,
But I mean, like, just if you have like that far off value, like say I didn't have a, if I wanted to know like the exact value of something on the plot, can I click on it and?
yeah. Oh, you mean click on it?
Yeah, is there-
No, you'll probably have to run
Just-
the case statistics.
Okay.
Yeah, you'll have to get that. Well, however, I would love you to all start learning more about these robust methods, robust regression or robust standard errors, which can accommodate exactly the type of problem we're talking about. So, let's stop there.
That was a good one. I enjoyed that.